This video is about how to compute the asymptotic variance using the Fisher information. Let's see what is the Fisher information and why we need it. We need it to compute the asymptotic variance. I have done another video previously where I have used the delta method to compute the asymptotic variance. But in this video, we are going to use the Fisher information. So here x1 to xn are some random variables which are independently and identically distributed, and it has a probability distribution p theta. So here true parameter is theta star, and if we want to estimate theta star, then we need an estimator, so that is theta hat. By the central limit theorem, we know when n approaches infinity, square root of n times theta hat minus theta star in distribution converges to a normal distribution with mean 0 and variance v. This v is known as the asymptotic variance v of theta hat. Then this v equals 1 over Fisher information. So usually Fisher information is denoted by uppercase I of theta. So this is the relationship between the asymptotic variance and the Fisher information. There are two ways to compute the Fisher information. Here we need the probability density function or the probability mass function. So if this is a continuous distribution, then we need PDF. If it is a discrete distribution, we need PMF. Then we have to write the likelihood for one observation. Here we do not need n observations, just the first observation like x1 would be enough. Then write the log likelihood for that observation. Then we can compute the first derivative of this log likelihood and then compute the variance of the first derivative. The second method is to compute the second derivative of the log likelihood and get the negative value of the expected value of the second derivative. So now from this method or from this method we can get the Fisher information. Finally we can get the asymptotic variance. So here I am going to take this as an example. Here I have a normal distribution with mean theta and variance theta. Now I need to estimate theta, which is theta hat. Finally the asymptotic variance of theta hat. Here this is the likelihood expression for one observation is L1, and then the log likelihood for one observation is lowercase l. I assume this L is twice differentiable. So from the first method, we have to take the first derivative of the log likelihood and then to compute the variance of the first derivative. So then the Fisher information is something like this. So it is I of theta equals variance of the first derivative of L with respect to theta. And from the second method, we can get the second derivative of log likelihood and get the negative value of the expected value of the second derivative. Then my Fisher information is this one. Negative expected value of the second derivative of the log likelihood. Finally, I can get the asymptotic variance as variance of theta hat is 1 over Fisher information. Now here we know that variance cannot be negative. So I have this variance, but in this case, if this L is concave, then the second derivative is going to be negative. That is why I have to put a negative sign in front of that. Then finally I can get a positive quantity. Now we can continue with the same example to compute the Fisher information and the asymptotic variance. This is a Gaussian distribution with mean theta and variance theta. Therefore, expected value of x is theta, variance of x is theta. If we have a Gaussian distribution with mean mu and variance sigma squared, so this would be the PDF or the probability density function. It is 1 over square root of 2 pi sigma squared times e to the power negative x minus mu squared over 2 sigma squared. So in our case, this expected value is theta, variance is also theta. Therefore, we can replace sigma squared and mu with theta, and this is the required PDF. 1 over square root of 2 pi theta times e to the power negative x minus theta squared over 2 theta. Now we need the likelihood function for one observation. It is L1 and it is f theta of x1. It is just this PDF. Then again we need the log likelihood function. It is L of theta. It is log of this expression. So this is like a product. So here we can write this square root 1 over 2 pi theta square root as 2 pi theta to the power negative 1/2. Then we can have two log terms here. So this is the first term and this is the second term. Then we can further simplify this one and we get x minus theta squared over 2 theta. Negative sign, this negative sign is here. Now take the first derivative with respect to theta. So again negative 1/2 log 2 pi theta is 1 over 2 pi theta times, again we have to get the derivative of this term, is 2 pi, and this is a ratio. Therefore this is a denominator times the derivative of the numerator minus numerator times the derivative of the denominator over denominator square. Finally, after some simplifications, we get this expression. Now, immediately we can take the second derivative. It is L double prime theta is 1 over 2 theta squared minus x squared over theta to the power 3. Now we have the first derivative of the log likelihood and also the second derivative of the log likelihood. Therefore, we are ready to compute the Fisher information. To compute the Fisher information and the asymptotic variance, I am going to use this easiest method first. Compared to the other method, most of the time this method is easier than the second method. So here Fisher information equals negative the expected value of the second derivative of the log likelihood. I have already evaluated this part, therefore I have to get the expected value and put a negative sign in front of that. The property of linearity of expectation helps in this case. That is how I got these two terms. Here negative 1 over 2 theta squared plus 1 over theta to the power 3 expected value of x squared. We know expected value of x is theta, variance of x is theta, and this is the formula to compute the variance of x. But I need the expected value of x squared. Therefore, I have to rearrange this expression. Expected value of x squared equals variance of x plus expected value of x quantity squared. So I know variance and the expected value. Finally, I get theta plus theta squared for the expected value of x squared. Now, Fisher information I theta equals 1 plus 2 theta over 2 theta squared. Now the second method. So I have to use the other formula. It is the variance of the first derivative of the log likelihood. Now again we have computed this term, and these two terms do not contribute, but only this term. So it is 1 over 4 times theta to the power 4 and variance of x squared. Now I have to evaluate variance of x squared. Here I use this formula, then I can replace this x with x squared. Then I get variance of x squared equals expected value of x to the power 4 minus expected value of x squared quantity squared. Then again I know everything other than this part. So expected value of x squared is here. So to solve this part, I have to get this one. So this integral from negative infinity to positive infinity, x to the power 4 times my PDF. PDF is here. and it becomes theta to the power 4 plus 6 theta to the power 3 plus 3 theta squared. Then finally this variance x squared becomes 4 theta to the power 3 plus 2 theta squared. You can solve this integral by integration by parts or by using an online integration tool. So now I can replace this variance of x squared with this, and finally Fisher information becomes 1 plus 2 theta over 2 theta squared. So I get the same result as here. Now you see that this method is easier than the second method. Always computing the variance is actually more difficult than taking another derivative, another extra derivative. In this case, we had to take the second derivative. So what we have to do is first get the first derivative and the second derivative and take the expected value and put a negative sign in front of that. Most of the time, this method is easier. Now I know by the central limit theorem this expression. Here V is the asymptotic variance, and asymptotic variance is 1 over Fisher information. Therefore, my asymptotic variance, that is variance of theta hat, equals 2 theta squared over 1 plus 2 theta. We can do this problem by computing the maximum likelihood estimator and then by applying the central limit theorem and the delta method. But in this case, we used the Fisher information.